All right, I'm going to go ahead and do this as a PowerPoint presentation. I got a lot of stuff to get through, and as always, I've got way too much, but I'll rush through it and see how I can do. So I'm going to share my screen. All right, so everybody, thanks again to Robert for bringing me on again. You know, there's a ton of stuff. We all know we need space fission power, you know, and generally for anything beyond you know, Earth orbit, up through a whole bunch of different science missions, surface power, large huge and outports, and eventually colonies and transportation to Mars to get us there quicker. But for now, I think we need to be focused on the more near-term stuff, and that I'm going to talk mostly about it at this point. And so I'm going to go through these slides quick, and I can get copies to people if they want them. The first point I want to make is how far we are from nuclear thermal propulsion. People tend to think we're going to have that sometime soon, but we need to focus on the chemical Mars direct kind of missions as something we can do sooner rather than later. And one of the reasons for that is you look at power density. This is a pretty detailed plot, but I have a temperature on the left and power density on the bottom. And nuclear thermal propulsion is way harder than any reactor ever conceived of. And during the rover Nerva days in the 60s, they did an unbelievable job and got to this point on the chart here, a test that was successful, but still a long way from flight. And so I want to point out how hard that is, whereas like the KRUSTY and Kilopower tests we did here in surface power systems will be in the realm of these green reactors that have actually been built and flown. So when you look at nuclear thermal propulsion, there's a lot going around about how all this progress going on, but there really isn't. You know, back in rover Nerva, they did 19 different reactor tests, and we're still a long way from flying. And they're a much lower specific impulse than what people are pursuing today. And if you get into the nuclear engineering, which I'm not gonna, is tons of differences between what people are pursuing today and what they did back then. And remember, what they did back then was get to 710 seconds of ISP with $10 billion in a regulatory environment we can only dream of today. And so it would take tens of billions just to get that test capability back if we get serious about NTP. And there's good reason to. At the end, I'll kind of summarize where all these things fit. But we're a long way from that now, so don't hang your hat on that at this point. And the trend lately is that nuclear electric propulsion is the future. I think NASA is starting to come around to that finally. But it's super hard as well. The human-sized NEP, if you're familiar with Franklin Chang Diaz's Bessemer, it needs a really sporty reactor, and so it's going to take a while to get there. And if there's two reasons why I think NEP will be where we end up, unless I made this caveat, unless Elon makes Earth the orbit and in space feeling so cheap and easy, we don't need anything better. Which, you know, in the long term. Still might be true. Right now, we definitely don't need anything better. And NEP can, the electric propulsion can evolve via simpler, smaller, useful systems, which will get us there through evolution. This drawing on the right would show, I'm going to turn on the pointer, you know, a system with a very high power reactor system that could be used for human and cargo transport to Mars. But that's not something we would succeed in trying to develop the first time out of the box unless we truly had an Apollo type effort. So we can evolve there, and it's game-changing performance, right? NTP gives us a factor 2 over chemical, which is great. But the NEP eventually gives us 5 to 10 times higher, more fuel efficiency, and maybe more. So it's where we would want to go regardless, and I contend through all my experience that it's a lot easier to get there than nuclear thermal propulsion. Until then, so this is what I really want to talk about, is you know, space reactors. The kind of stuff we're trying to work on now can do all sorts of stuff for us. And you know, all the science and NASA missions, as we know, I don't really have to convince anybody of this. You know, in a lot of potential commercial missions, you can use the power for all sorts of stuff. Pretty much everybody that proposes science or exploration on Mars needs power, right? And so this is just, you know, a slide that would show there's a ton of reason for this. Everybody knows it because we've tried to do space reactors for the last 50 years because we know we're going to need them. The question is how we're going to get there. And, you know, on Mars, and I'll do a comparison with solar in a bit, you know, but the hard part is really the dust storms and just the deployment of gigantic arrays and ability to keep them clean. And most of the easy water, you know, this will all depend on all the great stuff we just heard about, you know, where the easy water is. If it's at high latitude, solar becomes less attractive. But as you'll see, even at the equator, solar is not very attractive at high power levels. Then the moon, you know, the moon is really hard. It's always kind of ironic that I think the moon is harder than Mars for solar, unless you're going to just park yourself someplace where the sun always shines, which limits you pretty quick. So, you know, it's got the 14 days of darkness. So there's a huge need for these reactors in space. And, you know, as Robert's been pushing for years, you know, we really would like to have the reactor to make our propellant to leave Mars, and then all the cool stuff we want to do there. And that nothing's really changed fundamentally, except that we've got much potentially cheaper Earth to orbit costs, which is going to make this a lot easier. All right, so now the bad news. All right, so in the United States, we've had 40 years of stagnation in reactor technology, not just space reactors, but in terrestrial reactors. And you'll read all these wonderful reactor programs that are going on throughout the decades. And, you know, right now you'll see it all the time, all these new reactors that are under development. None of them ever get close to becoming a prototype, and maybe one of these current projects will. But, you know, and with space reactor programs, we spent billions, in terrestrial reactor, tens of billions with nothing. Why have they failed? Really is because they become too inexpensive, partially because of oversold paper concepts. And then, you know, the traditional source of spreading money and continually pursuing paper studies. You know, and I agree with Robert that, you know, mostly the aerospace companies and the labs just do what NASA wants to do to be a part of the game, and nobody pushes back when they're doing something dumb, as Griffin would say, you know. And so I'm trying to push back in some respects. It hasn't really been public political bias or regulation really is the first order problem. So this gets into what we're doing now. The Kilopower reactors, and you've seen in the past, and I'll show again briefly, you know, what we did there. But they produce about 1 to 10 kilowatts at low mass, and then maybe 25-30 kilowatts with low enriched uranium, which lets us run the fuel to higher lifetime because of nuclear burnup concerns. But they really can be building blocks to get us that first step. And I have one slide that shows how the technology approach evolves up to greater megawatt without any really significant change in risk perspective. So I'm going to talk a bit here about this Kilopower concept for Mars. This shows 4 of them buried on the Mars surface, and each of them providing 10 kilowatts. And I always have to make the public service announcement about space reactor safety because it's it always comes up. And you know, a reactor before it's operated is essentially benign. It's uranium, the same stuff we mine out of the ground. We enrich it to increase its activity a little bit, but it's totally benign until we operate it. So if there's a full dispersal accident, and let's say there's an explosion on the launch pad that completely disperses the entire reactor core, you're still below background radiation. So there's no risk from this reactor at all. And so it just needs to be, that point continuously needs to be made, that before it operates, it's got no risk. Once it operates, it becomes a nuclear system that you have to shield, and that's what we designed it to do. All right, so how did we get to this kilopower reactor and DUFF and KRUSTY? You know, we wanted something attractive and could be proven, and so we've done a lot of work with heat pipe reactors before, and I'll briefly go through that. That said, you know, we think this is a great technology to use for space reactors because they're passive and have high reliability and are easy to test. So the first thing we did was the DUFF experiment, which proved the concept, did the test configuration of what a system might look like, and really got things going. We were sitting around depressed like in 2012 as reactor engineers. We haven't done anything real our whole careers. And so we wanted to do something to show we could still do something nuclear, and it wasn't going to cost billions and billions of dollars like NASA had been convinced because of the past DOE programs that had showed them it's going to be billions and billions of dollars. And so we got a lot of data. We showed that we could predict what was going to happen, and we convinced NASA to go ahead to the next step and do a $18 million program to test KRUSTY. And this is what a kilopower reactor, 1 kilowatt, the smallest version of a kilowatt power reactor, would look like. I'm not going to go into a lot of technology and engineering since this is a pretty diverse crowd, but the nuclear fuels down here, heat pipes take the power up to Stirling engine converters that give us electricity, and then that's rejected to heat. And the cool thing about this reactor now is we actually built one and tested it, which is, again, the first time anything like this has happened in the United States in 50 years. So it's a very big deal that we've shown this is can be done affordably and that it worked. And so what really happens is, you know, fission is the process of a nucleus splitting into multiple pieces and releasing binding energy. This is actually a piece of the KRUSTY core. There were 3 pieces all stacked up. So it's 4 inches across. This is me holding it in my hands. So with all, it's just, you know, it's kind of like magic, right? I mean, power just shows up in this material because if you put it in the right geometry. And then what we did, the power conducts over to these slots where we put heat pipes. And a heat pipe was invented in Los Alamos partially as a way to do space reactors because they knew this was going to be a good thing, but mostly they're using laptop computers and all over society, usually water heat pipes, but this is a high temperature sodium heat pipe where you boil sodium down to the bottom, heat comes in from the reactor, and it condenses up at the Stirling engines in this case, deposits its power, then a wick will bring the sodium back, and you have a closed loop with unbelievably efficient heat transfer. The problem was nobody had ever operated a heat pipe reactor before, and we're a little worried maybe something weird would happen, and KRUSTY showed that it worked exactly as you would hope. Then the third component is a Stirling converter. The Stirling engine is a heat engine where the piston moves through an alternator to make energy. So this stuff, we all put it together, it all worked great, and that was kind of just to show quickly what the components were. We started with our flight concept, did a lot of prototyping. If you're an engineer, you know, you just want to get your hands on stuff and start building and see if it's going to fit together, how it's going to work. Then the great thing about the heat pipe reactor is we can do electrically heated testing. And so we were able to show the system would work. And then finally, we did a nuclear test where we put the system on a machine that could generate the nuclear power and create electricity from that nuclear power. And I got a few results to show there. First thing we did was, you know, benchmark our system with electrical testing. And this was huge from not only working out kinks in the design, developing our instrumentation and control, but really for the regulator. You know, you probably heard of the NRC if you're familiar at all with nuclear energy. In this case, it was the Department of Energy, but the regulators need to have confidence that your system's going to operate as you'd expect. And we also use this to benchmark the codes, eventually get regulator approval to actually do this test. This just shows, this is actually 3 of those core pieces. So this is our KRUSTY core, and these are the heat pipes that are in these slots, and we put these interference fit or strong shrink fit clamps to hold the heat pipes against the fuel. And then beryllium oxide is this white material, which is a great neutron reflector, which is what makes our system essentially airtight in terms of safety. You can't, this reactor won't go critical unless it's surrounded by this material. So there's never any risk of a criticality accident until you get it in its final configuration, and then you want it to go critical. And then this is assembling the core, stacking up our beryllium oxide, getting ready to go. We had our Stirling engines and a lot of thermocouples. For a test, you need a lot of thermocouples. So in the final configuration, we have KRUSTY in a vacuum chamber, because we needed to be in a vacuum chamber to simulate the low conductivity we'll get in space or on Mars, because Mars doesn't have much of an atmosphere, and we'll probably, we might take advantage of the atmosphere. We definitely will for our heat rejection, but whether we do for getting heat across surfaces, I don't know, because the stainless steel should be able to handle the atmosphere. This is really what makes the Kilopower reactors and KRUSTY unique. The first thing that makes it unique is it is the only reactor that's been tested in the last 40 years. That's saying something right there, right? But also that it's a load following system. We set the core temperature at 800 degrees Kelvin with our reactivity control, and here where the power conversion system, by changing the stroke on the Stirling engines, draws more or less power, and we get to the point where it just, if we draw less power, the core power drops and stays there. If we draw more power, the core power responds. So we're not controlling the reactor here. It's just load following, which is unbelievably great from a control perspective. We don't rely on any reactor control system or the ability to measure what's going on in the reactor. So it's perfect for autonomous operation. We also showed that we could fail a heat pipe, produce full power. Another transient where we just changed the thermostat temperature, as we call it, by changing the control. And the reactor, the heat pipe reactor, just was amazingly beautiful in terms of its response. The heat pipe's essentially an infinite conductor. And when we look at what we did with KRUSTY, the only difference was, instead of pulling out a safety rod, a startup rod, we inserted the reactivity by raising a reflector. And this gets into nuclear engineering details, but it really, as far as the reactor concerns, it doesn't care, because the mean free path of a neutron is so big that the whole core operates as what we call a point kinetic system. So we don't need any more nuclear powered testing for any of these systems. We just need to run it through electrical testing systems, testing our flight system to make sure it'll work. So this shows a picture of a lot of Kilopower reactors being deployed. Here's one where there's 4 on a lander. There's cases where we bury it. This case, we plopped one down and not buried it. And then, a lot of that depends on shielding and how close humans are going to be. In our baseline case, if we don't bury the system, we talk about having the outpost about 1 kilometer from the power source. And there's actually a fair amount of reason that the outposts will have to be 1 kilometer from a lot of your infrastructure, because where your rockets land, the debris from landing and takeoff, you might need to be 1 kilometer away anyway to prevent being hit by flying debris. So, but in a buried case, we can live right next to the reactor. This was something we put together for NASA a while back that wasn't pursued, to do a 10 kilowatt electric ISRU demo mission to demonstrate we could make propellants in oxygen with the reactor. So that's something cool we've thought about doing. I don't intend to go through this chart, but everyone always asks for a chart that shows how Kilopower evolves from tens of kilowatts to the megawatts. There is a path, but it's never that simple. And one of the problems, big problems that always goes on, is people want to focus on the 3 megawatt, system that we really might want someday, and make sure we can get there without any changes. But you learn as you evolve, and we grow into that system. We'd have various offshoots depending on where what we learn as we go. But the key is really that all these systems would be tied to KRUSTY, be tied to the nuclear operations, so we wouldn't need nuclear ground testing. This gets closer into our higher power systems. Costs is, mass and cost come down greatly as you increase power with reactor, because of how their nuclear reactivity criticality plays. This is a look at like 100 to 200 kilowatt Mars Brayton system based on our technology. And the cool thing here, you see a big cooling fan. This is actually to use the Mars atmosphere to reject our heat. It's tough because it's so low density, and actually you get a lot more power if you're one of the low elevation regions on Mars versus the top of Olympus Mons. But it's you have to draw a lot of air in, but it does work, and we think it's the way to go for these reactors. And also, when I talked about burying, we tend to think of burying in the reactor, if we can, pretty deep, 2.6 below the surface, is as deep as you need to get, such that you're basically, the reactor's way below the Mars background, the dose. And from there, you just decide how much shielding. If you can't bury that deep, you look for a crater, you look for a ridge. And this shows the relative size of different reactor powers. Now, mass is where it gets interesting, and that's what most people would want to look at, and really specific power. So the current, the KRUSTY systems are very low, and then when we start looking at these higher power Mars surface systems, we start getting in a pretty good watts per kilogram range, and actually start to level off. And one of the reasons that, well, there's a certain size of reactor you would launch and send to Mars. After that, if you want more power than like 5 megawatt reactors can give you, a bunch of those, you're ready to build your own reactors on Mars. I mean, or maybe just send the uranium. So the logical stepping point for any Martian civilization, from sending the power from Earth to building it there, is somewhere in the 5 megawatt range. This is a look at our 650 kilowatt Mars surface concept. Shows all the masses, shows the relative size. But as always, I got to hurry through because I want to get to a couple of the last slides. But what we did, we also designed a solar power array, and I really haven't seen many of these, which is funny because you'd think tons of people would be working on these. But so we looked at a 650 kilowatt rollout solar array and looked at various sizes and calculated the mass of those, including the battery masses and where it was deployed, and a lot of variables, which got us to this point where we look at the mass of 650 kilowatts of a nuclear versus a solar powered system. And this would be at the equator, and depending on the efficiency of your cells, and this would be at 40 degrees latitude. And it leads to this chart. I mean, nuclear, as most people would recognize, is unbelievably more efficient than solar on a mass basis, a cost basis, and having a robust power supply that won't suffer from like an incredibly strong Martian dust storm. And so we get into these watts per kilogram that are like 10 times better than solar, even at the equator. And this kind of shows, this is one of the old SpaceX colony kind of drawings. So this would be like when you have 20 people on Mars, you would have like 3 200 kilowatt reactors or that solar array. When say you had 300 people on Mars, you know, you would have, say, 10 650 kilowatt reactors instead of this solar array. Look at the mass difference, three times lighter for the reactors. And then when you want to go to 3,000 people, get really big, you know, the solar arrays is becoming pretty silly to try to maintain and clean and deploy, obviously deployment. And then it becomes a no-brainer. I mean, but even at the low powers, it is. All right, so my last thing, and I wanted to get to this, but I probably won't get much time, is I still can't believe how big a deal people make of radiation when it comes to Mars risk. And I know there's a speaker tomorrow, but when I looked quick at the death probability of certain events, I would say we're lucky in early missions. You know, if an astronaut maybe comes back with an 87.6% chance for being alive. That's just, you know, based on a lot of this. And then what the radiation is going to do for them, based on the linear no threshold models, what all the health physicists would say to you, is going to, in this case, give you a 2% chance the reactor is going to die cancer from the mission. But that's going to be from 5 to 25 years after they've completed their life's goal and are a hero. And then more likely they're still going to be in that case. So why would this risk of radiation be something people are very worried about? It's got to be put in perspective, and it's very small. In the last slide is even living on Mars. People make a huge deal out humans can't live on Mars, and you know, and we say, okay, well, we'll shield them. But even if you don't shield them, this is the life expectancy of a human on Earth. I came up with a model where I say there's a 1% chance a human's going to die acutely on Mars every year due to life support failures, food problems. And so this is how much risk the radiation adds. But we will be able to live underground or in a shielded facility, so that if you're only outside 20% of the time, the radiation is a totally negligible risk to everything else, and we need to keep that in mind. I'll stop there, and probably not have time for any questions, but thanks for listening.
Okay. In case of a mechanical failure of the reflector moving assembly, is there a secondary way to shut it down?
I'm not sure. Could you shut down the reactor?
Yes.
I didn't really get what you have a question of how we shut it down?
If the main mechanism fails, is there a secondary mechanism?
Oh, well, there's 12 control drums, and so if none of them work, or your control systems work, you won't be able to shut it down. But if I had more time, I'd explain how these kilopower reactors, the reactor shuts itself down. If you're not drawing power from this reactor, it doesn't produce power. So it basically shuts down all its own if you're not using it. So that's what makes it great.